Hey everybody, and welcome to our 13th video lecture. I hope you guys are all stoked for Stokes Theorem. Obligatory puns aside, Stokes Theorem allows us to compute various surface integrals in terms of line integrals, as well as to compute various line integrals in terms of surface integrals. In a very strong way, you should be thinking of this as some sort of generalization of Green's theorem, which also compared various area integrals to different line integrals. For Stokes' theorem, I want to think about a surface S. The boundary of a surface is this curve here forming the edge of the surface. So for example, closed surfaces don't have any particular boundary. So they don't have any border or any edge. So this curve C down here is the boundary of the surface S. Now if my surface is oriented, which is to say I've got a choice of direction for my local normal vectors, let's just choose this obvious orientation here. That also chooses an orientation of my curve, which is a direction for my curve. Do I go around clockwise or counterclockwise? And the way I want to think about that is the right-hand rule. So let me continue these oriented vectors all the way over to the boundary here. Now on the curve itself, I could go either this direction, or I could have gone this direction. If I go this direction, I want to think about my hand being in three-dimensional space, and I want to think about curling my fingers in the direction of that red arrow. In that case, my thumb of my right hand should point in the direction of the orientation of the surface. Or alternatively, just point your thumb in the direction of the orientation of the surface, and your fingers should curl in the direction that the curve should be moving. So in this particular case here, the orientation should be going around the edge in this fashion. And again, this is coming from pointing my thumb in the direction of the orientation of my surface and just curling my fingers. And the direction that my fingers curl tells me the way that the curve should go. If I chose the opposite orientation for my surface, the curve would move exactly the opposite direction. And what Stokes' theorem tells us is that the integral of the curl of a vector field over my surface will be equal to the line integral over that closed loop of f dot ds, or f dot dr. So this can be extremely useful because sometimes I can replace a very complicated line integral with a much easier surface integral, or alternatively a very complicated surface integral with a line integral that I have a much easier time doing. If I think about the special case, when my surface is just a flat patch of the xy plane, and my orientation is chosen so that it's just the obvious one pointing straight up. And if I point my thumb in the direction of that orientation, the boundary curve, which is just this curve in the xy plane, is also going to gain an orientation, just a direction that it moves. My fingers curl in this counterclockwise direction. And then in this particular case, Stokes' theorem is going to tell me that the double integral over that patch of the xy plane of the curl of f, and I'll just write dA in this case since this is just a patch of the xy plane, this will be equal to the integral over that closed loop of that curve of f dot dr. And this was exactly the statement of Green's theorem that we derived in that section when we talked about the curl. This was like the vectorized form of Green's theorem. So Stokes' theorem recovers Green's theorem in the case that my surface is just like a flat squashed surface in the xy plane, And it's just a generalization of that. I can do much more complicated, more interesting surfaces with it. Well, let's go ahead and do an example of Stokes' theorem in the case when my surface isn't flat. In this problem, I want to evaluate the integral over a curve C of this vector field that I've given, and where C is the curve formed by intersecting the plane x plus y plus z equals 1, and the cylinder x squared plus y squared equals 9. And I want to give that curve a counterclockwise orientation when I look at it directly from above. So that's the way that we're going to go around it. So I've drawn the cylinder x squared plus y squared equals 9 in blue, and the plane x plus y plus z equals 1 in green. And they intersect at a curve, which is a circle shape here, where this plane cuts through that cylinder. So that's my curve C, which is a circle kind of shape, or an ellipse kind of shape, inside the plane x plus y plus z equals 1. And I want to go around it counterclockwise when I view this from above, so that means I'm going around this way. Now my goal here is to calculate f dot dr. And a nice way to do this is to just use Stokes' theorem, which says that this is going to be the double integral over S of the curl of f dot ds, where S is this oriented surface for which C is the boundary. So we can see specifically that's going to be a flat surface here, which is this little ellipse type shape inside this plane x plus y plus z equals 1. And the orientation that it has to have is going to be the one so that if I'm pointing my fingers in the direction that the curve is going, my thumb should point in the direction of the orientation. So that should be the one where these things are pointing out this way. So this is the orientation of my surface. And I can also very easily calculate the local normal unit vector, which doesn't change because this thing is flat, right? That vector is going to be constant. Because I know that this surface will lie inside the plane x plus y plus z equals 1. And a normal vector to a plane from the plane equation is obtained just from ripping off the coefficients of x, y, and z. So the normal vector for this plane is going to be just the vector 1, 1, 1. And a local normal unit vector will be the vector n hat, which is just going to be 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. So the double integral over S of f dot ds vector can now be rewritten, and it wasn't f, it was the curl of f, there we go, is going to be equal to the double integral over S of the curl of f dotted with that local normal unit vector, which is just 1 over root 3, 1 over root 3, 1 over root 3, ds scalar. So that's a much easier integral to calculate. There's no more vectors involved after I take the dot product. So let's try to do that. And the last thing I want to do here before I start to, think about my surface more is calculate that curl. So f, again, was this particular vector field. So the curl of f is calculated in the usual way, and we get 0 x squared y squared. So the integral I'm trying to calculate is the double integral over S of x squared plus y squared over the square root of 3. And now what I want to do to get this integral is I want to parameterize my surface. But my surface is given by a function, so there's a very easy parameterization where I'm just going to take x and y to be u and v, so I don't even need to use u and v, I can just use x and y. And my surface is a plane, x plus y plus z equals 1, so z is going to be 1 minus x minus y. So r sub x is going to be the vector 1, 0, minus 1, and r sub y is going to be the vector 0, 1, minus 1. And the cross product, r sub x cross r sub y, is going to be the vector 1, 1, 1. So in particular here, rx cross ry, the local unit area, is going to be the square root of 3. And my parameterization here should be for all values x and y with x squared plus y squared less than or equal to 9 in order to be inside this particular cylinder. So I want to integrate over this particular domain. And I get that my surface integral finally becomes just the double integral over d of x squared plus y squared over the square root of 3 times the square root of 3 dA. This is just a nice easy integral in polar coordinates. It's integral from 0 to 2 pi, integral from 0 to 3, because I'm integrating over a disk of radius 3, of r squared times r d theta. And evaluating that, we get 81 pi over 2. So 81 pi over 2 was the original line integral that we were trying to compute. Let's do another example going the opposite direction. And in this example, I want to evaluate the double integral over S of the curl of f ds, where f here is this vector field x squared sine z, y squared xy, and S is that oriented surface formed by the part of the paraboloid z equals 1 minus x squared minus y squared, lying above the xy plane and oriented upward. So S is this surface with the bottom cut out, and the orientation on this particular surface is upward, so that these vectors are pointing outwards like this. And the one at the top is pointing straight up, and so on. You get the idea. So what Stokes' theorem says is that in order to do the surface integral, we could alternatively just do the line integral over the boundary of the surface, which is this edge down here. And I need to make sure I go along the right way. So if I stick my thumb in the direction of one of these normal vectors, my fingers are going to curl in this direction around the curve. So this is the way I need to go around the curve here. So to do this line integral, what I need to do is I need to parameterize that curve in the xy plane, curve C, and I need to make sure that my parameterization goes around counterclockwise in the xy plane there. And there's a nice easy parameterization for that. Now this is a parameterization of a curve, so it involves a single variable t, not u and v, right? Don't make that mistake. Now if I want to go counterclockwise in a circle, this is a circle of radius 1 here, I can just use cosine of t, sine of t, and that certainly does the job. So there's a nice parameterization of my curve, and t is ranging between 0 and 2 pi. So the integral that I'm trying to compute is exactly the integral over that closed curve C of f dot dr, which is going to be, I'm plugging in my x, y, and z values in for r. So technically here, r is going to be a parameterization of that curve in 3 dimensions. So what should my third value z be in order to get that curve in the xy plane? Well, I mean the clue there obviously is in the xy plane when z is equal to 0, so I'm plugging in z equals 0 for that. And when I'm plugging in these x, y, and z values in for f, I'm getting the integral over c of that f, so z is 0, sine of z is sine of 0, which is 0. So my vector field is becoming 0. Y is sine of t, so it's going to be sine squared of t. And z is going to be xy there, so it's going to be sine of t cosine of t. And I'm dot producting that with r prime of t. So let's fill that in too. R prime of t is going to be minus sine of t, cosine of t, 0. And I'm using the fact that this line integral is the same thing as the integral of f of r of t dot product with r prime of t dt. So I'm just writing this down then as an integral from 0 to 2 pi of this dot with r prime, which is going to be cosine t, r prime is minus sine of t, cosine of t, 0 dt, which is just the integral from 0 to 2 pi of 0 times sine of t, which is 0, sine squared of t times cosine of t, which is going to be sine squared t, cosine of t, and then sine t cosine t times 0, which is just 0. So it's just this, which is going to be 1/3 sine cubed of t evaluated from 0 to 2 pi, which is just 0. Now, one of the really cool consequences of Stokes' theorem is that the integral over a closed surface of the curl of f dot ds is always going to be 0. This is because there's no boundary of a closed surface, so by Stokes' theorem, this integral would be equal to the integral of f dot dr over a curve which is nothing. But another way to see it that maybe is more reasonable is to think about a limiting argument. So if I've got a closed surface here, I can make it a surface with boundary just by picking out a curve that I cut out here, C. This outer closed surface here is S, and when I remove C, I get a new surface which does have a boundary. And if I take the limit here as C shrinks, the limit of that surface, of the integral over the surface, minus the interior of C. So just the surface minus that red patch of the curl of f dot ds is just going to be the limit over C of the integral over C of f dot dr. And as I let C get smaller and smaller and smaller, this limit on the right hand side is going to go to 0, because I'm just integrating over a smaller and smaller and smaller curve, where on the left hand side there, the patch that I removed is getting smaller and smaller, so this is just becoming the integral over the full surface. So that's a really neat consequence of Stokes' theorem. If I already know that my vector field that I have is the curl of something, then when I do a surface integral of that vector field, I'm just going to get 0. So for example, if I had the problem calculating the surface integral of the vector field f, which is 0, 0, 2, over a sphere of radius 1, well, I can notice here that f is already equal to the curl of a vector field, specifically the curl of the field minus yx0. So the integral that I want to do over that closed surface is equal to the integral over that closed surface of the curl of minus yx0. And as we just talked about, the integral of a curl over a closed surface is always going to be 0. So boom, we're done. One particular consequence of this is that if I have a surface, let's call it S1, which is this blue surface here, and it has a nice boundary going around this way, and let's give it an orientation, which is this nice natural outward orientation. Or if I have a different surface, maybe like this green one here, which shares the same boundary, let's call that S2, and with an orientation which is outwards this way as well, well, I know that the integral over S1 of the curl of f dot ds vector plus the integral over S2 of the curl of f dot ds is going to be equal to the integral over that full closed surface formed by gluing S1 and S2 together. But the integral of a curl over a closed surface is 0. So this is going to be 0. In other words, the integral over S1 of the curl of f dot ds is equal to minus the integral over S2 of the curl of f dot ds. And that can be really, really useful. For example, let's think about calculating the double integral over S of the curl of f dot ds, where f is this vector field, and S is the upper half of a sphere of radius 1. So here's S, and in red here's the boundary curve. And let's give everything the usual upwards orientation. So that the orientation of the sphere is outwards like this. Since the problem didn't specify, this is just a choice that we're going to make. Now I calculate the curl of f to be the vector minus 2z times e to the z squared, 0, x squared plus y squared. And if I'm thinking about integrating that over the top of the sphere, that's going to get pretty complicated pretty quickly, because that e to the z squared function is not very friendly. But from what I just mentioned, I can relate that to the integral over a similar surface, or any other surface with the same boundary. And this green surface down here has the same boundary, and I just want to give it the appropriate orientation as well. So let's call that green surface down there S with some fancy hair, S twiddle. So that means that the double integral over S of the curl of f dot d s vector is going to be equal to the double integral over S twiddle of the curl of f dotted with ds vector. And these are compared, they're not quite equal, there's a minus sign difference between the two. And the local normal vector for that bottom one is just 0, 0, minus 1. It points directly downwards. So this is the double integral over S twiddle of the curl of f dotted with minus 0, 0, minus 1. So it's just going to be x squared plus y squared ds. So this is just an integral. Oh, and the minus sign went away. So this is just an integral in the xy plane over the disk of radius 1 of x squared plus y squared dA, which is really very easy to do. It's the integral from 0 to 2 pi, integral from 0 to 1 of r squared times r dr d theta, which is just pi over 2. So that's another really nice application of Stokes' theorem. But let's end there for now, and we'll pick up next time with our very last video lecture, which is going to be on the divergence theorem. So thank you guys for watching, and I'll see you guys then.